Hello and welcome to another video. In this video, we're going to be working on find all people with a secret. And in this problem, you're given an integer n, denoting that there are n people numbered from 0 to n minus 1. And you're also given a 0 index to the integer array meetings, where meetings states that there's a meeting from x and y, so 2 people, at time the third value here, so time t. And a person may attend multiple meetings at the same time. Finally, you're given an integer first person. Person 0 has a secret and initially shares the secret with a person first person at time 0. So this is worded a little bit weird, but essentially what they're saying is person 0 and first person will know the secret at time 0. And then every time there's a meeting, if person X has a secret, then they will share the secret with a person Y and vice versa. The secrets are shared instantaneously. That is, a person may receive a secret and share it in other meetings in the same time frame. Return a list of all the people that have the secret. After all the meetings have taken place, you may return it in any order. So let's look at a couple examples where the times are all different, like this one, for example. Like, let's say we just had a problem where the meeting times are all different, and you're going to see this is really easy to do. So in this first example, so the first person is 1, and remember person 0 knows the result as well. So person 0 and 1 knows the secret in the beginning. So in this first meeting, we can also, it's pretty obvious to sort the meetings by start time, because you really want to know when the people meet. So these are already sorted for you, but let's say they weren't, you would store the meetings, sort the meetings by start time, because you want to figure out when people actually know the secret, right? So in this first example, person 1 and 2 meet at time 5. Well, because person 1 knows the secret right away, person 2 will also know the secret at time 5. And then at time 8, person 2 and 3 meet. So person 2 knew the secret, so now person 3 will know it as well. And finally, at time 10, person 1 and 5 meet. 1 knew it, so 5 will know it as well. So you want to return 0, 1, 2, 3, 5 in any order. So if the meetings all occur at different times, it's really easy. You just check, does one of the 2 people know the secret? And if they do, then the second person does as well. Now, the tricky cases are going to happen when meetings occur at the same time. So I think there's a couple examples here, and yeah. So let's look at example 2. So for example 2, person 0 knows the secret right away. That's always the case. And then person 3 also knows the secret right away, because person 0 shares it with this first person. And so now if we go by meetings in sorted order by start time, so this is going to be the first one that happens. So 1 and 2 have a meeting at time 2, but 1 and 2 both don't know anything at time 2, so this doesn't matter. Then at time 3, person 0 and 3 meet, and person 3 and 1 meet. So 0 and 3 meet, but 0 and 3 already met before, so they already both know the secret, so this doesn't matter either. And then 3 and 1 meet, so 3 will tell 1 the secret, so you want to return this right here, 0, 1, 3, or 0, 3, 1, or so on. Let's look at the last example. So the last example, the people that know the secret right away is 0 and 1. And then the 2 meetings that occur at the start is, or not at the start, but at the same time, at the earliest, is 1 and 2 and 3. So this is kind of like the tricky case, and this is going to get complicated if you have a bunch of these. So because 1 meets with 2, 2 will learn the secret at time 1, so 2 will be added. And because 2 learns the secret at time 1, 2 can also pass that secret on to 3 at time 1. So 3 will also know the secret at time 1. And finally, at time 2, 3 will meet with 4, and 3 knew the secret, so 3 will pass it on to 4, so you want to return everything. But yeah, essentially, hopefully this makes sense why, if the meetings were just all at different times, if there were no 2 meetings at the same time, really easy problem, you would just sort increasing start time, and then for every xy, check if x or y knew the secret. If yes, then add other person to result. And it's really easy. You can just have a set or something, right? So every time you have a meeting in increasing order, you just check okay, if one of these 2 people knows it, then I'll add the other person to my result set. But the tricky thing is if you have a bunch of meetings at the same time, and that's kind of the thing we need to know. So let's say person 0 and 1 know the secret, and then at some time, doesn't matter what time, but let's say at some time, 1 has a meeting with 2, 2 has a meeting with 3, 3 has a meeting with 4, 4 has a meeting with 5, and so on. So something you can't do is you can't just say, like, let's say all these meetings occur at time 1. You can't just say, like, for every meeting that occurs at some time, if one person in all of these is in my result, let me just add all of them. They won't work, because you can have a situation like this where you can have 6 meets with 7 and 7 meets with 8, let's say, and these all occur at the same time, right? So these all occur at time 1. Well, what you'd want to have in your result after this is 1 and then 2, 3, 4, 5, right? Because 1 will tell 2, 2 will tell 3, 3 will tell 4, and 4 will tell 5. And these are irrelevant. So you want to be able to do this efficiently, and it's kind of difficult because you don't, like, how do you sort the meetings? There's really no good way to do it, because let's say the people that did know, let's say instead of 0, 1, 2 knowing in the beginning, let's say like 5 only knew the meeting, right? Out of all of these, right? Only 5 knew the secret. Well, you would loop through and you'd say like, okay, well, no one knows it here, no one knows it here, no one knows it here. Okay, this person knows it here, so I'll add 4. But then how do you, like, if you did a loop, you would basically have to keep looping a bunch, right? So then you'd have to loop again, like here, 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 here. Oh, the 4 knows, so I'll add a 3, and so on. And that's kind of the main problem, is how do you do this efficiently? Like, given a bunch of, I guess we can try to simplify this problem, right? So given a bunch of edges and some nodes that are in the result, how do we put everything else that's connected to these edges in the result? And that's kind of the problem. So we can write this down. So given some edges with some nodes possibly being in the result, return all nodes that are connected to those nodes efficiently, right? Like, we want to be able to do this. Basically, you have to be able to do this in O of n. So if you're given n edges, you have to be able to do an O of n, because the meeting's length is 10 to the 5th. So worst case scenario, like, you have to get like an n or an n log n or something solution. Like, you can't do a nested loop. You can't just keep looping through these and checking for a connection until there's no connection, because that would take way too long. And so the easiest way to do this is a multi-start BFS. There's a bunch of ways to do it, but essentially it's a multi-start BFS. And basically our idea is going to be, let's say all of these occur at the same time. So we can just, every time we can get the meetings, and we can put them in a dictionary by meeting start time. So the dictionary will have meeting start times, and then for that meeting start times, we'll have all the meetings. So basically, like for this example here, let's say at time 1, we'll have these 2 meetings, and then at time 2, we'll have this meeting. And we can just take the start times and sort them in increasing order. And then for every single different start time, we can get these edges, right? So for every single different start time, we can get these edges and build a graph. And the way that's going to work is basically we're just going to build a undirected graph, right? Because if you can go from 1 to 2, you can go from 2 to 1. X can tell Y the secret, or Y can tell X the secret. You can traverse it in any way. So let's build this graph really quick just to draw it. So we have 1, 2, there's an edge. 2 has an edge to 3. 3 has an edge to 4. 4 has an edge to 5. And 6 has an edge to 7. 7 has an edge to 8. Obviously, this can be a more complicated graph and so on. But essentially, the way a multi-start BFS works is you can have a BFS that will have every single node that knows the secret. So in this case, it's only 1, but it's possible to have multiple nodes that know the secret. So if like 1 and 5 knew the secret, you would start with 1 and 5 in your BFS. So you have a BFS, and in our case, it just has 1. Then basically, and you make sure into your BFS start nodes, you only put nodes that are in the result, and you only put them in one time. So you're also going to have a visited set to make sure that for each node in the meetings, you only put it in one time max. Because if you put it into the BFS, that means we visited it. That means it can go into the result. And so we don't need to put it in multiple times. But we do need to put in nodes that are in the result, because they might be able to visit other nodes. So we're going to have a visited set and a BFS, and this is just a normal like BFS with a visited set. Then we just traverse starting here to every single node. And so like from 1, we would see like, okay, what are all the edges that 1's connected to? Oh, look, 1's connected to 2. Let me put 2 in the BFS. Let me put 2 in the visited set, right? So I'll have like 1 and 2 in the visited set. And everything you visit in your BFS, you just add into your result. So at the end of your BFS traversal, just like a basic BFS traversal, you will have all of these nodes in your result. And that's kind of like how you solve this problem. You just basically, for every single different time, increasing order, you build a graph. You start with every single node that is in the result, and you just BFS. And in multi-start BFS, the code is literally the same as a one node start BFS, right? Because if you think about it, like let's say we have a graph like this, 1, 2, 3. So if we start with node 1 will be in here. But once we actually process node 1, then 2 and 3 will be in here. So the BFS will contain multiple nodes. So multi-start BFS is literally the same thing as a single point. You just put in multiple start nodes, and then the rest of the code is exactly the same. And that's kind of the idea to get this to work. And like I said, in order to get this to pass, you need to make sure that you only put nodes into your BFS one time. And then that's literally it for the problem. Is you just sort it by times, and then for every time you do this, you go through all the meetings for that time, and then you put in all the nodes that know the secret in the beginning into your result, or not into your result in your BFS, and you just traverse to every node possible. So let's take a look at the code for this. So we have a result, and the way I have it is I have a result set, because you want to be able to check, does your person know the secret efficiently, right? So I just use a set. So the two people that know the secret right away, like I said, is 0 and first person. Then we have times, which is just going to be a dictionary of meetings and their start time. We go through all of our meetings and we append them to the times dictionary. Then we order the times that we have by increasing order, right? Because we want to look in our meetings in increasing order. Then basically we take every time that a meeting occurs, we set up this BFS, right? So we have a BFS, we make a visited set, we make a graph, we get all of the meetings that occur at that time, right? We have to process all of those, like every iteration of the loop, we'll process all of the meetings that occur at that time. So we just make a basic graph, right? So for X and Y, that in the meeting, make an edge from X to Y, make an edge from Y to X because it's undirected. And then we check if X is in the result, meaning if X knows the secret, and it's not in visited, meaning we haven't put it into the BFS yet. Let's put it into the BFS and let's add it to the visited set. And the best practice usually I found for BFS is add things to the visited set right when you put your item into the BFS, because it's not a heap. You don't need to like wait till you remove it because it's first in, first out. So add everything to visited right when you put it into the BFS. That's what I did here. Same thing for Y. If Y knows the secret and we haven't visited Y yet, we'll add Y to the BFS. This ensures that like let's say 1 and 2 know the secret. If you have like 1, 3, 1, 5, 1, 6, and so on, you don't want to put 1 into your BFS 3 times, right? You only need to put in once. Then literally as basic of a BFS as you get. So while you have a BFS, pop the node, check all the neighbors. If the neighbors haven't been visited yet, add them to visited, add them to the BFS, and add them to the result, right? Everything that you process in your BFS will know the secret because you are starting at nodes that know the secret, and every node that's connected to those nodes at that time will also know the secret at that time. Then finally, at the very end, we just return the result. So that's basically it. So we can run this. And yeah, it is important to not forget this part. I think this is what caused TLE for me for again. Because like I said, let's say you have some extreme example where you have a bunch of meetings where it's like 1, 2, 1, 3, 1, 4, 1, 5. What I ended up doing is put in 1 into the BFS like 4 times. And then that made it too slow. So just make sure when you do the BFS, it's very easy to not have like duplicates. And the rest of the problem isn't super hard. So I don't think it's like too hard of a hard problem. You just basically have to realize like, how do I, given a list of edges and some nodes in those edges that are in my result, how do I figure out what nodes from those edges are in my result in OFN using a BFS? You can use other stuff too. I think you can use like union find and things, but this was like the super straightforward solution to me. So we can submit this, and you can see it's pretty fast. You could probably cut out some memory by like saving a few of these things. Like I probably didn't need to use like this array and things, but it's not too bad. Like I can just put it here. So I can just like throw this here and things like that, but it doesn't make too much of a deal, right? So you could do something like this as well. But regardless, let's think of the time and space. And it is kind of hard to come up with time and space for these like kind of complicated graph problems. I think these are like the hardest for like heap or like a bunch of different things you do in a graph, but regardless. So let's take a look. So for for every meeting, we're going to process it into a list, right? So that's already O of M, where M is the meetings. And then we sort the times. So worst case, the times is like, let's say every meeting occurs at a different time. So worst case, that's going to be M log M. And we do a BFS. So essentially every meeting only gets processed one time. And then we might put like nodes from that meeting into a BFS one time. But this BFS is basically going to be dependent on how many meetings we have, not how many nodes, right? Because like we can have like 1,000 nodes, but if we only have like 3 meetings, it doesn't really matter. So it doesn't matter how many nodes we have. It's more dependent on the meetings. Now, obviously, if we have less nodes, then we're not going to put them in like that many times. So if we have like 1,000 meetings that all occur at the same time, but we only have like 3 nodes or something, then it's going to be very fast anyway. But regardless, this basically just depends on the meeting. So I think it's actually just going to be M log M for the time. And then for the space, so we have the times, which is just going to be for times we're going to put in meetings. So that's O of M. And for the BFS, like we can't have more nodes than meetings. So that's also going to depend on M. So I think this is just going to be like O of M. You can say maybe it's like M plus N or something. But like I said, realistically, it mostly just depends on the meetings. And yeah, it's going to be all for this one. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.